afternoon, everyone. Thanks for coming to my talk. I want to just discuss quickly the research that is being presented here was done by myself and my coworker, Jared Riddle, who's out here in the audience somewhere. So if you have any questions afterwards, please feel free to hunt one of us down and ask that question. And without further ado, let's get into Badgerboard, Weaseling out the unknown. So I want to start with a little bit of a story, a little bit of a history lesson, I guess. 6 years ago, I was actually on the main stage presenting work that I did at Idaho National Lab, where I co-authored a paper about the general state of industrial control system security tooling. This was something to be used as a reference material for someone who wasn't really sure where to look for information. It just had general information about what security vendors were claiming they could do, where they operated the best, and what their success was expected to be. Really all self-reported. And what's interesting about this is, even though this paper is 6 years old, I think it was something that was really useful at the time. This is where OT security was. People really needed something to understand where to even look to get information. As a funny anecdote, while I was preparing this talk, that paper actually got sent to my brother-in-law in a completely unrelated field to the one that I currently work in. And so people still use it today. That might not be the most useful document at this point because we've seen a lot of maturity. And honestly, I think if that talk were to get submitted today to S4, you wouldn't see it actually hit the main stage. And that's both a good thing and a bad thing. We've seen a lot of maturity in the OT tools that we see today. We have gained a lot of vendors, lost a lot of vendors, but realistically, the tool set that we have is generally similar across the entire space. These OT tools rely heavily on asset inventories and passive network monitoring to determine when you have a possible adversary in your network. And realistically, I think we're at the point now where the grass is starting to get a little greener. But that being said, I think we also have not seen a lot of innovation in the current state of affairs. We see a lot of people talk about how we're going to secure the PLCs of tomorrow, how we're going to change the architecture to be more secure. But we need to worry about today and what the industries are utilizing and will be utilizing for the next 20, 30 years. Likely those are devices that we've already manufactured and put out into the field. So with that being said, that's something that's kind of stuck with me even after I left the lab system and came to Talos to do vulnerability research. But that being said, I kind of bounce this idea off my coworkers time and time again. And as such, one of the things we've really come to the conclusion of could be a good step forward would be a visibility IDS or IPS module. Obviously, the work that we do supports Snort because we're from Cisco. And as such, we've kind of waffled on and off again about how do we make Snort see more and get closer to the root of truth on these networks. So this visibility module, obviously, it would gain visibility into these internal networks. When you see IT tooling that's adopted today, it would be completely unacceptable to have visibility to a certain switch on the network and then ignore everything behind it. That's essentially what happens today in OT networks. All of these PLCs are effectively routers and switches with multiple modules on the backplane that communicate to each other, and we have absolutely no visibility into what's happening. Finally, final pro would be that this module is something that's easily retrofit into current installations. So while tomorrow's PLCs are going to be more secure, and that's great, this is something that we could actually deploy today into working systems and reap the rewards from. Now, not every great idea is just that great. There's definitely some cons with this, and one of them is this is just a small step forward from what we've kind of adopted as an industry. We have passive network monitoring. We're just one step lower. We're seeing more network, but we're not at the host-based detection of each module. In addition, this is going to be something that's very difficult to implement because there's many, many vendors with many, many protocols, none of which are documented publicly. So one of the things that we really looked into was how easy it would be to market this as a third-party security vendor. And the answer is, it's almost impossible. Most of these vendor backplanes are walled gardens. You have service contracts that guarantee that there's no way an end user would plug in a third-party product into their backplane without major repercussions from the vendor that they purchased from. So with that, we came to the conclusion that this was really infeasible to develop, and we started on it anyways. So we spent a couple months working on this, and honestly, we're standing on the shoulders of giants here. This research is really similar based on, as a starting point, the Weasel board that came out of Sandia National Labs. This was pitched as a zero-day exploit detection device for PLCs, and it focused on the Allen Bradley Control Logix 5000 backplane and the S7300 backplane. There's 4 entire paragraphs in this document about how backplane networks operate, and that is said completely tongue-in-cheek. The amount of work that is required to understand how these backplane networks operate is enormous. You need to find out all the different pins, you need to find out what they do, the general idea of how to capture that digital logic and lift it into a state that you can actually operate on. That being said, I have the utmost respect for the researchers that worked on this, and if you haven't read this paper, I would highly recommend you do so. About half of it is based on their specific protocol, but the first half of the paper is really interesting to read about how they really went about this process. And second, really where Jared comes in is his previous research on the M580. In 2018, he disclosed 32 unique vulnerabilities that have since been patched, and as such, I consider him one of the foremost experts on UMass. He might not agree with me, but it was very helpful during this research. And as you might have guessed, the device that we decided to do this research on was the M580 and the X80 backplane. Now, it's important to note here, we chose Schneider Electric. Part of the reason, and honestly the whole reason, was because we had this hardware. We're fairly fortunate in the research that we get to do, but it doesn't mean that expensive hardware is any easier to come by. So since we had this for vulnerability research, we decided to really do this just as a complete secondary research goal, just to see if it was possible. So what's specifically interesting about the Schneider Electric X80 backplane is that it has 2 separate communication buses that it utilizes. There's the X bus and the Ethernet bus. Each of these buses are 40-pin connectors on this backplane, and the Ethernet module, or the Ethernet bus, is a newer bus that has been introduced in some of the most recent generations of Schneider's PLCs. Not every device supports this protocol. Not a whole lot of information is transmitted over this bus, but it's still there and somewhat interesting. And then we have the X bus, which is really the more interesting topic of this research. So starting off with the X80 Ethernet pinout, out of this 40 pins, we have a 100 base T connection. So with 4 pins, 2 twisted pair on an Ethernet cable, a soldering iron, and some free samples from Molex, we have one of the world's ugliest Ethernet connections. And what we can do with this, just to verify that we have actually connected to this backplane, is capture some traffic. We can see once we've connected to the backplane that there is multicast traffic that is broadcast across the entire layer 2 switch that is the backplane. And it contains some basic information about this backplane, specifically what it supports, the different buses that it supports, firmware revisions. Realistically, most of this is not super interesting for what we were doing. But it is interesting because you can take stock of what this backplane is actually running. One of the downsides of this being a layer 2 switch, and this is not unique research by any means, is that you can do ARP poisoning on this backplane. And there's nothing special about this. Once you have the Ethernet connection, you can do simple ARP poisoning. Just as an example, you can see that 10.100 is the interface that we're capturing on, and we can see the network traffic between a client and the M580. Specifically, this traffic is looking at the M580's HTTP server through the network module on the backplane. One of the reasons that you wouldn't necessarily want to do this step in production is the Ethernet interface is actually somewhat documented by Schneider, and you can set up span ports on the M580. This is not necessarily a one-to-one integration of the traffic that's seen on this exact bus, but it is useful in the terms of not having to do ARP poisoning on a production network or on a production PLC. And then we move into what I consider kind of the more interesting bus. This is the X bus, and this is the proprietary bus that has most likely been developed in Schneider for many, many generations of PLCs. There's probably some changes over time, but realistically, this has been something that has existed for a long time, and there is zero documentation about this. Out of these 40 pins, there are roughly 6 that are of the utmost interest to us, starting with the active pin. The active pin is required to be pulled up to 24 volts because this is used from a quad channel buffer on the backplane to physically enable one of these ports. You don't want to be running signals out to all of these different pins if there's not a module that actually inhabits that specific bus. So as such, once we pull this pin high, we actually can see traffic on these pins. And we'll start with the control traffic. So the control traffic is roughly 500 kilohertz. This is important because when we're sampling this data to measure, we need to, as a rule of thumb, measure roughly 4 times faster than the signal is occurring. That allows us to make sure that we are capturing every transition of rising and falling edges. If we don't do that, that means that we can get corrupted data, and we don't really have any way to verify if the data that we have is exactly accurate or not, because that's what we're building with this research. In this control traffic, there's specifically the module's address that is claiming the bus. And this occurs in time slices on the backplane. And this is useful because we can actually tell how often a module wants to talk on this bus. This is something that we can do some statistical analysis on and determine, is this module talking more than it should be or less than it should be? Or are there changes in certain time frames? So this is kind of the first useful piece of information we've pulled out of this for a security aspect or baselining this information. And then we move on to the X-bus clock signal. And this starts to introduce a lot of issues with capturing. Specifically, we start with a 12 megahertz clock rate. That means at a roughly 4 times sample rate, we need to measure at 50 megahertz. This is getting into the realm of one dedicated microprocessor or microcontroller core, while a 500 kilohertz signal you can generally measure on a Raspberry Pi with Linux in Python without much concern. This is the speed at which you need to start worrying about how efficient is your code. Maybe you need to find a faster microcontroller or look into alternative hardware implementation options. Another thing that makes this clock unique is that it is actually pushed directly from the module that wants to talk on the bus. And it also deactivates completely when it is, before it is started and after it's complete. This makes it exceptionally difficult to measure because if we want a microcontroller, we need a clock to measure it or to run that processor off of. In this case, if we tried to use a microcontroller directly clocked from the backplane, then we wouldn't be able to do any processing when a module is not trying to push data. Additionally, one of the interesting aspects of this is that it is only guaranteed that this speed works for modules that we tested, which was specifically the network module. Each module could, in theory, push their own clock rates for this data. That would require further research, and those aren't modules that we had while doing this. And then finally, we come to kind of the lumping it all together of the X-bus data itself. So there's nothing specifically interesting here about how the data line is used. This is a open sync bus, which means that's active low. And what's interesting here is that we have to see the control message. Once the control message is completed, then we have specifically 5 clock cycles before data is pushed onto this bus. That gives us an important sentinel value while we are trying to pull this data out and reconstruct it to make sure that we're actually getting the data that we expect. And now that we've gone into all of the physics of actually capturing these digital signals, we need to build an actual implementation to do so. So what we decided to do was due to some of the concerns that I mentioned earlier, is use of FPGA implementation in order to capture this traffic reliably. The benefits of this FPGA implementation mean that we can actually dual clock this setup. So it is capturing data specifically on the rising edges and is completely in sync with the backplane module that's trying to push data. In addition to that, we can connect it to a microcontroller that is clocking it externally so that we can actually communicate with this module while the backplane module itself is not pushing data. This introduces a lot of complexities, as all FPGA developers will be able to tell you. You need to worry about synchronizing these clocks across boundaries and synchronizing the data across those clock boundaries as well. What's also interesting here is this backplane module is responsible not only for measuring this data, but actually also buffering the data across different messages and each clock cycle. This data is buffered internally to this module in bytes and then dwords. And once this data is actually ready to be read, it can trigger an external interrupt. And that external interrupt can be consumed by any number of implementation-specific microcontrollers. But the approach that we took was utilizing completely Xilinx-based microcontrollers. The idea here is that this is the easiest way to set this up. You could also use a RISC-V processor. You could use an external processor. It really doesn't matter. The details of this implementation are not important, and that's why it's really difficult to see this slide. But what this gives us is that we can actually use the Ethernet and UART, as well as the backplane reader, as directly memory-mapped peripherals in this microcontroller. And as such, we have the ability to run at memory speeds for these microcontrollers when we need to exfiltrate data from the backplane to a higher level for processing. Essentially, what we can do is utilize no-copy buffers to directly ship this information over UDP to an external processor that we used for further steps. And so this is where we start to get to a higher level of programming. We're not worried about the FPGA at this point. In our proof of concept, we use a Raspberry Pi to unwrap this data and turn it into something more meaningful. So at this point, we have this data off of the XBus. These XBus packets are roughly 48 bytes in size. Obviously, the last one's a little shorter if it has remaining data. And it's important to note that these messages are occurring extraordinarily fast. Each backplane will generate roughly 1,000 of these packets per second without anything occurring on the backplane at all. This is just information for acking different types, acking modules being present, making sure that timing is accurate, and most importantly, this is all done in hardware on the real device. The microcontroller or microprocessor that is running in the M580 actually offloads this to custom silicon for interacting with this XBus and doing all the physical layer. So when we capture a bunch of these packets together, we can start doing some analysis. And this is really where Jared's expertise was a godsend. We can start looking at this and identifying where UMass might be. And the reason that we know it's UMass is basically because it's fairly easy to spot once you know what you're looking for, starting with hex 5A. So in the first parts of these packets, we have XBus physical layer header information. We're not necessarily worried about what that is or how it interacts, because all of that is, again, done in hardware. And as such, it's mostly unimportant for the work that we're trying to do. Next, we see that we can have the XBus payload length, and this is going to be how long the UMass message actually is. We have source and destination fields, which are where the module is in the backplane itself. And then we have a flag that just represents that this data is, in fact, UMass, and you need to process it as such. Finally, we have the start of the message for UMass, and we move on to the second packet. In the second packet, we have very minimal physical layer overhead and just a big chunk of the UMass packet. And then finally, we have the remaining UMass data. So when we highlight it all against the original packets, we see where things start to really fall out and make a lot of sense. We can see that we have partial strings in this packet from the X bus, and once we have recombined them all using these headers, we can see that we actually have a string that makes sense. And this UMass packet specifically is querying the active project on the M580. This happens through the web interface, but this communication happens over the X bus. And this is where you see a lot of differences in what information is shared on which bus, and why it's important to see both of them. And so at this point, we moved on to recovering this data from the recovering this data and moving it into the IDS. For our proof of concept, obviously we were focused on Snort, but realistically this can be done with any network monitoring tool that exists. First step was to wrap this UMass that we newly recovered from the X bus and move it into Modbus TCP. This is just an easy way to wrap this and spoof it over TCP so that Snort can properly inspect it and alert on it. And so a lot of the discussions that I made today, and a lot of the choices that we made are specific to our implementation. But realistically, this is not useful or not the most perfected implementation there is. A lot of these options could be changed. Specifically, the most base form of what we need is a hardware device that is on the backplane that's responsible for extracting data from the backplane and encoding it into bytes. It needs to be very, very fast. This could be an FPGA or an ASIC. Alternatively, you could look into newer technologies such as state machine-driven PIO from the RP2040. That would likely be fast enough to interact with this backplane directly. It's also important to note, as I stated before, that these backplanes are extraordinarily noisy. So you need to filter this data or have a device that's fast enough to keep up with line speeds. Filtering this data could be done in the hardware, such as on the FPGA, or it could be done on the processing hardware as well. Most of these messages that occur on the backplane are not all that interesting from a security context, and as such, you're better off eliminating these from visibility sooner rather than later. And then finally, you need an integration for hardware and software, which is responsible for actioning upon the stream of data that is being generated by the backplane. In our example, this is a separate processor. As I said, this is going to be a Raspberry Pi that is unwrapping XBus messages and then rewrapping them into Modbus and being able to send them wherever you want. And also in our example, the Raspberry Pi is shipping this over loopback, but in reality, what you'd want to be doing is shipping this directly to a security sensor that would then be ingesting this data and alerting on it if necessary. So what's next, and where's the code? We wrote a blog that will inevitably be more useful than this talk. This talk is kind of trying to fit 10 pounds of information in a 5-pound sack. This blog is roughly 30 pages where we talk about all the technical challenges that we faced, all the different choices that we made while we were going through this, and also contains a link to all the code that we used. What we really want to achieve here is to release this code and see adoption in the community, but it's important to note that this code is not perfection. It's a proof of concept. Our day job is vulnerability researchers. This is kind of a side project that we thought would be really interesting. So this is just an example of how to implement the next layer of security solutions, and it's really a call to arm for end users to go and ask their vendors, why isn't this implemented? Why can't I see this information? And really try and get the conversation going about why this would be important to see and expose this information to security vendors. So what are the takeaways here? Most importantly, I think there's an industry-wide benefit to opening proprietary protocols of these backplanes. And I don't necessarily mean that we need to expose all of the documentation or go with torches and pitchforks to the vendors and demand that they change the protocol to something else. What we do need is to see and have the visibility into protocols that are operating over these proprietary buses or can be utilized and integrated into our current security tooling. Also important to note that product availability is driven by end user demand. If you ask, it will come. And it is possible and quite honestly, quite easy for us to improve our visibility in these field devices without a massive effort. PLC vendors can easily integrate this functionality in an officially supported module. The module that we implemented is officially read-only, and it cannot physically write to this bus. You can utilize this type of read-only device to verify your network modules. You can see device firmware updates. You can see logic changes, and you can verify all of the communication between your modules. But alternatively, if you wanted a faster time to market, you could do this with a firmware update, and your network module could now expose information to security vendors in order to alert on it more directly. They have all of the information, the vendors have all the information they need to easily expose this information, and it's really up to the end users to push for this to become more open. And with that, are there any questions?
Hi, do you characterize the backplane as a switch? Is it a switch or is it a hub?
Sorry, what was the last part of that?
Is it a switch or is it a hub? Like, is it transmitting to everything and things are just not listening?
It is a layer 2 switch, but it is not a complete hub in terms of not everybody sees everything unless you follow that ARP poisoning step, and then you can see data from the other modules.
Thank you.
Okay, thank you so much, Carl. Thank you.